Why is it important to study nonlinear structure formation in Horndeski gravity, and how can we practically do so? These are the questions that I'm going to answer in this talk, so if those interest you, then please keep listening. Hi, my name is Wright. I'm a postdoc working at Queen Mary University of London. This research has been done in collaboration with Tessa Baker and Ashim Sengupta, who are also at QMUL, Georgios Valogiannis at Harvard, as well as other members of the LSST Beyond WCDM topical team. So, what's the motivation behind this research? As I'll explain later, linear structure formation is well understood for Horndeski gravity, and codes exist that allow us to constrain Horndeski using observations of large-scale structure in the linear regime. However, nonlinear structure formation in Horndeski is not well understood, and the Horndeski n-body simulation codes that are needed don't yet exist. This is a big problem for current and upcoming large-scale structure surveys such as DESI, Euclid, and LSST, because most of their constraining power will come from the nonlinear regime. As I'll discuss later, it can be much more efficient to constrain Horndeski gravity rather than individual modified gravity theories, but this won't be possible for nonlinear structure formation until the Horndeski n-body code exists. Currently, our only options are to throw away the majority of the amazing data from these surveys and get linear constraints on Horndeski, or to get nonlinear constraints on the small number of individual theories that we do have n-body simulations for, such as F of R and DGP gravity. The demand for Horndeski n-body simulations is clear. Before I go any further, I think it's important that I break down the terms in the title of my talk. What is Horndeski gravity, and what do I mean by nonlinear structure formation? If you're already familiar with these terms, then please feel free to skip ahead a few minutes. The technical definition of Horndeski gravity is that it is the most general description of a four-dimensional scalar tensor theory of gravity with second-order equations of motion. But what does this mean in practice? Let's look at the Horndeski action shown here. In this short talk, I won't be able to explain it to you in full detail. Instead, what I want you to notice is that the action consists of four key terms, featuring four functions: k, g3, g4, and g5. We can map a variety of individual theories of modified gravity into the Horndeski framework by specifying different forms for these four functions. These include well-known theories such as F of R and Galilean gravity. A point to remember for later is that viable modified gravity theories typically need some sort of screening mechanism to suppress their modifications in high-density regions and allow them to be compatible with solar system constraints. Horndeski gravity encompasses theories that feature a variety of screening mechanisms. A big advantage of Horndeski gravity is that if we can constrain it, then we can potentially rule out multiple individual theories at once, making it a much more efficient approach than constraining individual theories one by one. Now let's move on to the second part of my title, nonlinear structure formation. The standard picture of large-scale structure formation is cold dark matter clustering under gravity in an expanding universe. Mathematically, the cold dark matter can be viewed as a density field with perturbations around some average density. When these perturbations are relatively small, we can treat them as being linear. In this regime, the equations of structure formation are simple and can be solved using a variety of methods. However, as structure forms, the density perturbations become large, and we must treat them as being nonlinear. In this regime, the equations of structure formation are more complicated and are typically solved using an n-body simulation. In the quasi-linear regime, between the linear and nonlinear, it may be possible to use higher-order perturbation theory. However, the limits of validity will still need to be verified by comparing the predictions against n-body simulations. Now that we understand a bit more about Horndeski gravity and structure formation, let's look at structure formation in Horndeski gravity, but in the purely linear regime for now. Here, structure formation is well understood using the effective field theory approach laid out by Bellini and Savitsky in their 2014 paper. Starting from the Horndeski action we saw in the introductory slide, they derived and linearized the field equations. They then showed that linear structure formation in Horndeski is controlled by 5 functions of time, the Hubble factor, and 4 EFT or alpha functions. These 4 alpha functions are just combinations of the k and gi functions from the action that appear grouped together in the linearized field equations. Each of these alpha functions has some physical meaning. For example, alpha m is related to the variation in the effective Planck mass, while alpha t controls the deviation of the speed of gravitational waves from that of light. Different individual theories within Horndeski gravity have different forms for these 5 functions of time. Several Boltzmann codes that compute linear structure formation in this framework exist, such as Hi-Class and EFTCAMB, and these have been used to get linear constraints on Horndeski gravity. So, we've seen that linear structure formation is well understood for Horndeski gravity, and codes exist that allow us to constrain Horndeski using observations of large-scale structure in the linear regime. However, neither of these points are true for nonlinear structure formation in Horndeski. I've already explained how this is a big problem for current and upcoming large-scale structure surveys, because most of their constraining power will come from the nonlinear regime. We discussed earlier how it can be much more efficient to constrain Horndeski gravity rather than individual modified gravity theories. This won't be possible for nonlinear structure formation until a Horndeski n-body code exists. Other people have recognised this problem and are tackling it in similar ways. I'd particularly like to point out the recent work of Hassani and Lombrizer and Dan Thomas. So if we do want to create n-body simulations for a general Horndeski gravity, how do we go about it? The key quantity we need to be able to compute is the screened fifth force between the n-body particles. We can estimate this with an approach involving a screening factor and coupling, as seen schematically in this equation. As well as being time dependent, the screening factor is also density dependent, so produces scale dependent growth, whereas the coupling only has a time dependence. This approach has been used before, in n-body simulations of individual theories of modified gravity. In our case, the screening factor and coupling can be computed from solutions of the background. Importantly, we can solve for the full Horndeski background, rather than assuming an exact lambda CDM expansion history. My collaborator Ashim is working on a code that will solve the full background and compute the screening factor and coupling for an arbitrary Horndeski action specified by the user. Now that we have this pipeline for computing the screened fifth force, we just need to implement it in the simulation code. For this project, we've chosen to implement it in an approximate Koehler simulation code, which we call Hi-Koehler, standing for Horndeski in Koehler. I won't explain the Koehler simulation method in detail here, but in brief, it makes use of Lagrangian perturbation theory to allow us to trade accuracy at small scales for overall speed, while remaining accurate at large scales. My collaborator Georgios and I both have extensive experience with Koehler codes, so it made sense to build on that experience here. While our Horndeski Koehler code won't be accurate down to the smallest scales, it should still be accurate down to around k of 1h over megaparsec, which is a serious improvement over linear theory, and certainly enough to validate higher order perturbation theory with. So, what do the screening factor and coupling, and their product, look like? In this plot, I show each of these dimensionless quantities for 2 different theories. Our first theory is a simple cubic Galilean model that we get by picking a simple form for 2 of the Horndeski functions, k and g3, as shown in the bottom left panel. With this cubic Galilean model, we then enforce a de Sitter-like attractor behaviour, where the effective dark energy will dominate at some point in the future. This reduces the freedom of the model, such that instead of choosing both k1 and g1, we choose just a single parameter, EDS, which is the value of the Hubble parameter at this future de Sitter point. The second theory shown is DGP gravity, specifically the normal ghost-free branch, with an enforced lambda CDM expansion history. Although we don't solve the DGP background using our Horndeski code, the theory still has a neat expression in terms of a screening factor and coupling, which is why we use it here. In the plots, the screening factor is in the top left panel, and the coupling is in the bottom left panel, while the product of the two is on the right. The cubic Galilean model is shown by the blue lines, while the DGP model is shown by the orange lines. Overall, it's clear each theory has a different redshift evolution for both its screening factor and coupling. Remember, the screening factor is density dependent. In these plots, the solid lines represent a low-density linear regime, and dotted lines represent a high-density nonlinear environment. The solid lines in the top left panel show that in the low-density linear regime, the screening factor is high, which corresponds to negligible screening as expected. Conversely, the dotted lines show that in the high-density nonlinear environment, the screening factor is lower, confirming our expectation that screening is actively suppressing the fifth force here. The contrast between the 2 modified gravity theories is seen most clearly by comparing the blue and orange dotted lines. In the cubic Galilean model, the screening factor decreases at late times, which means that the screening gets stronger, whereas in DGP the opposite is true, and the screening effect weakens at late times. Now let's shift our focus to the behaviour of the coupling in each theory, shown in the bottom left panel. Remember, the coupling is not sensitive to density, so the solid and dotted lines overlap in this panel. Here we see that the behaviour of the coupling at late times is similar in both models, where it increases as it approaches redshift 0. However, in the Galilean case, there is a clear bump in the coupling at intermediate redshifts. Finally, let's look at the product of these two dimensionless quantities, shown in the right panel. The greater the value of this product, the greater the strength of the fifth force. Once again, we see some density dependence due to the screening factor. The fifth force is stronger in the low-density linear regime in both theories because, as we saw in the top left panel, the screening is weaker. However, when we compare the two theories, even though the screening at late times was weaker for the cubic Galilean model than the DGP model, the product is larger in both density regimes. This is because the coupling at late times is larger in the Galilean case, and evidently this wins out against the larger screening factor, leading to a stronger fifth force overall. We can now investigate how these differences in the screening factor and coupling translate to the nonlinear matter-power spectrum as measured from the cold-dark matter distribution of our very first Hi-Class simulations. Feel free to go back to the previous slide to remember how the quantities that control the strength of the fifth force varied. In a slight change from the previous plot, the line star in this plot no longer refers to different density environments. It is only used to further differentiate between different modified gravity theories. Our Galilean model is represented by the solid blue line, and the DGP model by the dotted orange line. We have also run an F of R Kohler simulation, whose power spectrum is shown by the green dashed line. In this plot, we are showing the difference between these modified gravity power spectra and a lambda CDM power spectrum at redshift 0, such that the way all of these lines deviate above the y=0 axis demonstrates that they are enhancing the clustering of dark matter, as expected due to the effect of their respective fifth forces. At large scales, where we are in the linear regime and screening is inactive, we see that both the DGP and Galilean models produce an approximately scale-independent enhancement, whereas the F of R model produces a scale-dependent enhancement. As we move towards smaller scales, where the density is higher, there is a clear turnover in the orange-dotted DGP line due to the screening strongly suppressing the fifth force. In contrast, the screening seems to have a milder effect in the Galilean and F of R cases, leading to the enhancement plateauing at smaller scales rather than decreasing. This Galilean behaviour may seem surprising, given that the previous plot indicated that the screening should be stronger than in the DGP case at late times. However, remember that the stronger coupling in the Galilean case is winning out against the screening factor here, leading to a stronger fifth force overall compared to the DGP case. Creating this Hi-Class code and running our first simulations is really just the start of this project. We have a lot of work to do verifying that our approach for the screened fifth force yields results that are accurate compared to standard n-body codes. Necessarily, we can only do this at fixed points in Horndeski parameter space that correspond to well-studied modified gravity theories such as F of R and Galilean gravity, where standard n-body simulations already exist. The other piece of the puzzle is the code that Ashim is working on, which will automatically solve the background and compute the screening quantities for arbitrary Horndeski actions. This will obviously be an extremely powerful tool once it is complete. Before I finish, here are some take-home points. It's very efficient to constrain Horndeski gravity, as doing so can rule out multiple individual theories at once. However, it's currently impossible to compute nonlinear structure formation in Horndeski. This means the vast majority of large-scale structure data from current and upcoming surveys will be squandered, since we can't do the required nonlinear modelling. To solve this problem, we need to create n-body simulations for Horndeski gravity. To this end, we have found a way to estimate the screened fifth force for general Horndeski using a screening factor and coupling computed from the full Horndeski background solution. We have implemented our approach in an approximate Kohler simulation code that we call Hi-Class or Horndeski in Kohler when we've run our first simulations. There's a lot of work still left to do, but we hope to be able to share more results with you in the future. Thanks very much for listening, and I hope to see you at the live discussion session. You can also reach me via email at w.wright@qmul.ac.uk or via Twitter @BillWrightCosmo.